Hello everybody, my name is Wee and today we're gonna discuss about the keycard problem, which is an advanced problem. So you should know some things about bidimensional arrays, which are called matrices, and some beginner and intermediate knowledge such as conditionals, loops, variables, and so on and so forth. We also recommend that you know functions because there are some things in this code which we'll have to repeat, and rather than just rewriting them every time, you could just use functions. So let's get started. Let's consider Anton a worker that has a special plastic keycard with many different holes in it. This keycard can be represented as a matrix with n rows and n columns which only contains zeros and ones. So 0 might mean space and 1 might mean plastic. So his job is to check X different other keycards and see if they match with Anton's, no matter the orientation. For every keycard, there will be outputted a 0 if they don't match and a 1 otherwise. Now this might be a bit hard to understand, and well, when we're gonna see the example, so about right now, well, we're not going to have a good time, will we? This looks very primitive, we do not really know what's going on, so we have to go a bit deeper. Before trying to solve the problem, we should first explain it and understand it. This is the way we should treat any problem, not only this one, no matter how complicated. So let's get into it. In the given example, we can see that n equals 3, which means that Anton's keycard is 3 squares in height and 3 squares in width. So this is how the keycard would really look. But this is a representation without the holes in it. We also know that there are 2 more keycards which we have to check with the first one. So x equals 2, and here are they represented as a red and a yellow keycard. Now let's draw the holes in them. So here are the keycards with the holes. Now, the second one really looks a bit similar to the first one. If we rotate it counterclockwise, we can see that we get the same figure. Now, this is the exact same thing as the card that Anton's given. So, unfortunately, this cannot be said about a yellow keycard. No matter how much we try to rotate it or flip it, we will never get the same result. No matter how much time we put into it, this will never be the same keycard. So let's think of this problem a bit differently. Let's take a general keycard. So we do not really know if it has holes in it or if it doesn't. And I also indexed every square inside it. So the first one is 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is a general keycard. So 1, for example, can either be a hole or just the plastic, as well as 6, 8, 9, and so on and so forth. It doesn't really matter. So this is a general keycard. Now, what operations can we do to it? We can rotate it. So we can rotate it 4 times, actually. So we are going to get 4 different results in total. But we can also do one more thing to this keycard. We can also flip it. Now, if we flip it, we can then have 4 more rotations, and here are they. Now, you can see that the first ones I've rotated counterclockwise, and the other I've rotated clockwise. I have actually done that on purpose, so that we can see one more relationship between these keycards. Exactly, they're flipped with one another, so this is how the final thing should look like. Now this might not really be that relevant right now, but in the end, this will really be the key. So here is the final picture. In here we can see all the possibilities of the positions of a certain keycard. So now we have to make a choice. We can check the original keycard with all the states of a given keycard, so this might mean x times 8 operations in total, or we can flip and rotate Anton's keycard 8 times and then check those with a given keycard. So this would mean only 8 operations in total, which is very much an optimization. So this is the thing that we're going to go with. So we're not going to rotate every keycard, we're just going to rotate and flip the original keycard. Once we've done that, we only have to take an example and see if it works. So let's take this, a keycard, which we don't really know if it matches with any other thing in here. So we're gonna check it with every other possibility. So we're gonna check it with the first one and we're gonna see that it fails, the second one and it also fails, but the third one will be the correct one. And this is how this algorithm should work. Now we should talk about the two keys, the two real keys that will solve this problem. So these are the elementary operations that we've already used and discussed. So these are the rotation and the flipping of a card. So let's talk about the easier one. This is the flipping. We're still working on a general case, so this is still a general keycard, but this is fine. Now we're going to talk about an easier flipping, which is called the vertical flipping. So we're only going to flip this thing vertically. So how do we do that? We can just think of every row as the same color. So we're going to do that. So the first row is blue, the second one is yellow, and the third one is red. Now flipping will only mean this. This is the whole thing. Now, how do we do that in code? Well, we have to first take a bigger example so that we can see what's really going on. I'm not really going to take a keycard, I'm going to take a normal matrix for this, which will not really resemble a keycard because it will not have the same number of columns and rows. So this is the example that I'm proposing. And here we have a 3x9 keycard, well, 3x9 matrix actually. So we're going to index every line. And now we're going to see that the red one is the middle. We're going to ignore that for now. In order to flip this thing vertically, we just have to make pairs of two rows. So for example, 3 and 5, this would work just fine. 2 and 6, 1 and 7, and 0 and 8 would also be good examples. So this is how this thing would be flipped. Now, what relationship can we find in the rows that we've selected in a group? So for example, what relationship is between 3 and 5, 2 and 6, 1 and 7, and so on and so forth? Well, if we look close enough, we can just change the index of the latter ones. So 5, 6, and 7, and 8 could be rewritten as n minus the number that we want to change the row with minus 1. So the 3 will be converted to n minus 3 minus 1, 2 would be n minus 2 minus 1, and so on and so forth until we get to the final one. So this is how this thing would look like. Now, how do we write that in code? Well, if we were just to write this, this is how it would look like. It would be a 4 inside a 4, so this is all the code. Now we can see that we've got an auxiliary variable in there. This is used so that we can swap the things, but if we know the swap function, this is the code for you. It's way easier and nicer and way cleaner. And this is the whole function. We do not have to discuss this anymore. As a side note, we also know that this algorithm would work if n is odd or n is even. It doesn't really matter. So now we have to discuss the more intimidating part, the rotation part. So this is this thing. So again, we're back to our example, a normal keycard, and here it is rotated counterclockwise. Now I'm going to talk about the rotation counterclockwise because it is way easier. Now we have to make some very hard observations in here in order to reveal the final algorithm. So I warn you, this is not going to be easy. If you don't get it by the first time, you should re-listen to this 1,000 times until you get it, or just think about it yourself, because it's not that simple and it's not something that you come up with every day. Now, it might be better if you take a bigger example, for example, a 4x4 or a 5x5 or so on matrix. So that would be as well working, but well, here it is in a 3x3 version. So the first thing I'm going to do is I'm going to write the coordinates of each and every little square inside every keycard, and this is how they would look like. Now that we have done that, we have to make a very weird observation. So what happens in the width in the first example will happen in the height of the second one, and what happens in the height will happen in the width in the final result. So we have to see this. These are some arrows that might point that out for you. Now, what does that mean? Well, it means that the height will begin to be actually an x. So y will be x. So this is the relationship. y1 will be x2. You can see that in the formula below, I've used the notation J for both y1 and x2 so that this will be easier. So we're going to use the notation I for the y coordinate of m1. Now, what relationship will be between I and the ramming parameter for m2? Now, this is a bit harder, and this is what you have to understand. If you look close enough, you will see that it is n minus I minus 1. Sounds familiar? Well, it does, because it's similar to what we'll find in the flipping zone. And this, my friend, is the final formula. This is what we have to use. And well, if we were to look at the code, this is how it would look like. It's not a complicated code. So just thinking, this formula was harder than the actual code. The code is quite simple and it's easy to use. So now that we've got the rotation and the flipping, we can just assemble them together and we can just rethink the whole program. So now there is almost nothing left to do because we've discussed about anything that was important for this problem. So what we have to do is we're going to have Anton's keycard and we're going to have to flip it. Then we're going to rotate it, we're going to flip it, we're going to rotate it, flip it, and so on and so forth until we get all the 8 possible combinations of the certain keycard. Now I'm going to leave the code for you to do. Say what? Yes! Because this isn't that complicated. This is actually quite simple and it's good practice for you to remember these steps. So this is it. This is where this video ends. I might leave in the end a link to the code, to the actual code, so that you can see if you've done it correctly.